4.3 Riemann sums and definite integrals. So the quiz you just took was on indefinite integrals, and when we use the power rule or trig rule, the antiderivative is not unique. And what that means is there's an infinite amount of solutions, and that is what the plus C is used for. It represents what we call the general solution to a differential equation. And what's a differential equation? It's the derivative. Okay, so now the definite integral. We spoke about this very briefly. What does this represent? This represents a geometric approximation of the area. What is this notation for? Sigma means sum. So when we add up, we looked at left and right endpoint rectangles. When we add all them together, we get an approximation of the area. We looked at lower sums and upper sums. Now what if we take the limit? So as those number of approximations get more and more and more, then the limit makes the approximation become the exact area. And that exact area is what is known as the definite integral. So we set it up the same, the integral of f of x of d of x. Now notice we have boundaries as part of the integral. So a is the lower bound or the lower limit, b is the upper limit, and this function here, the definite integral, will evaluate to some number. That number can be positive, negative, or 0. So indefinite integral, our answer was the antiderivative. It was some general solution. It was still a function in terms of x. Now the definite integral, when we have boundaries on our integral, our answer, this will evaluate to a number. Okay, so in words, what does the definite integral represent? It's the region bounded by the function f of x, the x-axis, and the vertical lines x equals a and x equals b. So you guys have already done this. You did this on your last quiz, and again, that was the left and right endpoint approximations. And what did that do? It approximated some area bounded by a function. You could think of the x-axis, that's the important of the dx, because that's what you're integrating with respect to. And then x equals a will be your lower limit, x equals b will be your upper limit. So a is always less than or could equal b. Okay, so the area bounded by some function and two vertical lines, x equals a, x equals b, is represented by this definite integral. So set up a definite integral that represents the area of the shaded region here. Do not evaluate. So the integral, the boundaries of the shaded region, -1 to 2. What's the function that's graphed? 2 to the x power, and that function is in terms of x. And that's all that this is looking for. We don't have the tools to integrate that yet anyway, and if we wanted to approximate it, then we could use left and right endpoint sums, and we could get a lower sum and an upper sum approximation. So to evaluate a definite integral, then we need to use known geometric formulas. So we know area, triangles, squares, rectangles, trapezoids, circles. So any one of these can be used, but how are we going to determine what to use? Set up a graph. So what does the definite integral represent? Being able to identify all these things from the definite integral. My function is f of x equals 2. So the region bounded by that horizontal line, the vertical lines 0 and 3, and the x-axis. So what's the area of this region? It's just the area of a rectangle, base times height. So that definite integral evaluates to 6. For this function, 1 minus absolute value of x, that's a vertical shift up of 1 unit. If I plug in -1, it gives me an x-intercept. If I plug in +1, it gives me an x-intercept. So now we're looking for this area, bounded by the function, the x-axis, and -1 to 1. Those would be your vertical lines that bound the region. So what's that area? It's a right triangle with a base of 2 units and a height of 1. So this definite integral evaluates to +1. That represents the area of the region bounded by this function between those two values. Okay, properties of definite integrals. We don't always have a function or something that we can draw a graph of, so properties give us important information about a function. If you attempt to evaluate the definite integral where the boundaries are equal, if you think in terms of area, there would be no area there if you start and end at the same point. The integral from b to a of f of x, your boundaries always need to be written low to high, and a is always less than or equal to b. So in order to switch the boundaries from a to b, you take the opposite of the integral. If you're attempting to evaluate a definite integral from a to b, you can split that integral into 2 separate integrals. So as long as this value c is between a and b, then we can evaluate that integral and add it to the value of that integral. And where the one integral leaves off, the next one needs to pick up. So those upper and lower bounds do need to be equivalent. The definite integral of some coefficient times a function from a to b, just like derivatives, we can bring that coefficient in front of the integrand, integrate, and then just multiply whatever that value of k is. And we've already sort of looked at the last property with this one. If you're integrating 2 separate functions, as long as you're adding or subtracting those functions, you can break those integrals up. As long as the boundaries are equivalent, these 2 statements are equal. Okay, so given the definite integral from 0 to 5 of this function, it's assigned a value of 10, and the integral from 7 to 5 of this function is equal to 4. So just knowing these 2 pieces of information and using our properties to evaluate this, notice that the boundaries are written bigger value to the lower value. So we just take the opposite of that. This is given as 10, so the answer to part A is just -10. 0 to 7, now notice we have 2 things going on here. The integrals both have a 5 in them. This integral, though, in order to write it from lower limit to upper limit, we just take the opposite of the answer that's given. So we can split this integral from 0 to 5 f of x dx, and then add to that the integral from 5 to 7 f of x dx. So we're still looking for the integral from 0 to 7, but we know 2 pieces of information. From 0 to 5, the integral is 10. From 5 to 7, the value of that integral is -4. So the final answer is 6. Part C, whenever the boundaries are equal, that evaluates to 0. Part D, we have a coefficient now. So whatever the value of the integral is, we'll just multiply it by 4. We found that answer from part B, so 4 times 6 would give us 24. And using the same property, bring the coefficient out front. The integral from 0 to 5 was given originally as 10, so this evaluates to -20. Okay, so evaluate the integral from 1 to 3 of this quadratic, and we're given these 3 pieces of information. So I'm going to split the integral up. I I have 3 terms in the integrand, so I'm going to break it into 3 integrals. Now using the properties, -1 is really just a coefficient. 4 is a coefficient to the x. And then I can bring the 3 out front as well. Integral from 1 to 3 of x squared is given as 26/3. Integral from 1 to 3 of x is given as +4. And the integral from 1 to 3 of dx is given as 2. Plus 16 minus 6. So 4/3 would be the final answer. Okay, so that's all I have. If you want to attempt this one for homework, this is what we'll start with tomorrow in class. And I believe it's number 44 in the book. All right, enjoy your day.